pretty soon. And so let me do actually a little, of course I always talk about what I talked about last time. I'm going to go a little bit further backward if no one has any questions. We're okay. It's like only half of you are showing up. It's freakish. Anyway, okay, so there's a reason we start this class with Maxwell-Boltzmann because it gets you immersed in probability. To be blunt, it really isn't that hard. It's just a bunch of constants. And quantum mechanics, which is really what this class is it's a paradigm, I think that's the right word, a paradigm of probability. Okay, so let's review Maxwell-Boltzmann because it can help you because it's all probability. And you have to use probability in the way it should be used for Maxwell-Boltzmann and quantum. They have some synergy. But if you don't recognize their differences, they can butt heads and you can start shedding points. Okay, so as a review, Maxwell-Boltzmann, notice I've written net velocity, that there's no such thing as negative net velocity, so it looks like I'm integrating the Maxwell-Boltzmann distribution over all possible velocities. What is the answer? Huh? What do you, Left Shark, what do you guys say? You guys are the quiet ones. What is the integral of the Maxwell-Boltzmann velocity over all possible velocities? What is this number? 1. Okay. Now, just to throw you off a bit, I actually put in the Maxwell-Boltzmann. What's this?
Oh, that's the average calculation?
So what?
Average calculation.
Right, now how do you know? Because this is the Maxwell-Boltzmann, and it's multiplied by v, it's integrated over all velocities, so this is average velocity. Of course, you don't have to memorize that that's square root of 8 kt over pi. I remember that because I've done this like 7 or 8 times, okay? It gets drilled into you eventually. If I ask you this, the thing to look up is an identity, and don't forget the constants. Anyway, we've done that. All right, so you got this. Distributions integrate to 1. That means that probability goes from 0 to 1, 0% to 100%. So that's rather obvious. It's just a check that you've made the probability distribution correct. Distributions times the thing that they distribute give averages if integrated over all possibilities. We could even do this, right? We can square this. If for some reason we feel like we need to know this, and there are reasons that we need to know this, because we can relate that to the average energy. 1/2 mv squared is the energy of a gas, so this is useful. Okay, so that's just review. Now let's get back to what we talked about last time. How about wave functions? Well, obviously I'm going to talk about the Schrödinger equation, but I also mentioned a little bit about wave functions towards the end of the class. I am integrating the wave function over all possible values. The answer is?
Probability distribution.
Well, just give me something. What do you think?
1.
1? What does Right Shark say? What do you think? Remember we talked about how wave functions are probability distributions. So what does it integrate to? Huh? Oh, you say 1? You're all wrong. Every one of you is wrong. Why are you wrong? It's not normalized.
So it's 4 times.
No, you can assume it's normalized, but wave functions are not probability distributions. Wave function squareds are probability distributions.
Is that psi or is that 4?
A psi. That's, I'm trying to make it generic. So we were doing cosine kx. I'm just trying to not make all wave functions cosine right now because we're going to have tons of different wave functions, obviously. Okay, don't forget that. Wave functions squared are probability distributions. All right, now, therefore, you can do things that you already know. Now, I'm assuming that the proper limits of integration are minus infinity to infinity. I've not really specified what this is, so we'll just say that it goes from minus infinity to infinity. And as usual, I would make that clear in the question. Okay, this is
The average.
all right, average x. There you go. Right. Everything you learned in Maxwell-Boltzmann applies to this wave function stuff. Don't forget to square it because that is how everyone misses points on the first test and the final. is you cannot get it straight, whether you square this or that, or basically you end up not doing either. And so that means you missed the wave function. So look out for that. So wave function squares are probability distributions. This would tell you the probability of finding a particle at a certain position. And I'm going to draw some more examples of that. And I'm kind of going backward in terms of how I did the lecture in terms of my review. So those are wave functions. It kind of made sense to start with wave functions because we were talking about Maxwell-Boltzmann at the beginning of the class. Okay, then the Schrödinger equation itself. Actually, maybe the way I'm ordering this little review makes sense because I mentioned to you that quantum mechanics is a very strange thing because it's all about the Schrödinger equation. But you almost never solve the wave functions with the Schrödinger equation. Almost never. You figure it out by other means, and then the Schrödinger equation actually gives you the energy or some other thing that it's useful for some other thing. And that's just weird. Anyway, okay, the Schrödinger equation, you can look at this second order differential equation and say, oh my God, but what really is just kinetic energy plus potential energy is total energy. Now that is very simple. You learned that, I don't know, some physics in high school, but hopefully you knew it before then. Okay, we're going to just not worry about potential energy. We're going to describe an electron in outer space all by itself. In fact, we'll just say that it's an electron in a universe, and there's no end to the universe, and there's nothing else in the universe. Just, I don't know, why not? Just make it insanely simple. We're not going to worry about even a galaxy that's 1,000 parsecs away. Okay, now, we work with, so forget potential energy. We have kinetic energy is equal to the energy. Now, this is where I walked you through how Schrödinger constructed kinetic energy. It actually, it's not just 1/2 mv squared, how do I figure out velocity, and how would that work? P squared over 2m is 1/2 mv squared, obviously they both have to be energy. Momentum is mass times velocity, and in what when you learned about Isaac Newton, when you took mechanics in high school, maybe high school, or definitely as undergrads, you learned that the derivative of position with respect to time is velocity, and therefore p squared, here's about the 2m anyway, p squared would be mass squared, the double derivative of position with respect to time. That's m squared v squared, right? Question?
Wouldn't it just be the derivative squared, not the second derivative?
Is it?
Yeah.
Huh, no, I'm not too sure. Well, that'd be, yeah, because double derivative would be acceleration, wouldn't it? Yes. But then you could turn the acceleration into energy too, because that's force. Ma is force times distance. Anyway, it's a beautiful mosaic. All right. Okay, now I want to point out something to you. I'm not going to walk through the derivative of momentum again. I'm just going to tell you what it was. It was the double derivative of position. Now, what I was trying to get you to focus on here is you always think of like, well, you have derivatives in mechanics class, derivative of time, velocity. Velocities give you accelerations or 1/2 mv squared. But do you notice that I'm getting kinetic energy by the derivative with respect to position, right? That's like what? In mechanics in Newton land, which we would say the correct academic term is to say classically. Classically, this would be the derivative of time, but instead I have the derivative of position. Classically, the derivative of position corresponds to probably nothing. In quantum mechanics, it's everything. Okay, so anyway, I just want to point that out. It's really actually more funky than it seems, but remember that the whole point of this was to suck the, let's do cosine kx. Kx is, of course, 2 pi over lambda. So I'll be explicit. What this does is, this gets a 2 pi squared over lambda squared. This double derivative operates on this wave function to withdraw the 1 over lambda. And then I've got the de Broglie relation satisfied. Unfortunately, the double derivative of a cosine happens to produce a minus sign, so we cleverly just multiply by a minus sign to get rid of it. Remember that the de Broglie relationship says that momentum is h over lambda, which is h bar over 2 pi over lambda. Sorry, that's h, which is h bar, 2 pi over lambda. So I feel like I've done, have I done that? Yeah. Okay, so anyway, what we have to do is we kind of need to do something about that 2 pi. We need an h, so let's multiply by an h, but we also need to worry about that 2 pi. So what we end up with is an h bar squared. That takes care of p squared. Oh, and don't forget the 2m, and that had to be there because p squared over 2m is energy. So again, let me summarize. The 1 over 2m is there. The minus h bar squared satisfies the de Broglie relationship. And you never really see Planck's constant. You never really see Planck's constant in quantum mechanics. You always see an h bar. And the reason is, it's a silly reason, is that all the wave functions have 2 pi in them. They've always got to have a 2 pi, because when you travel a wavelength, you need to have gone from 0 to 2 pi. So to wipe that out, it just become h bar. It's not important. It's just that, again, unfortunately, wave functions have to have a 2 pi in them. So we just, we kind of knock that, we reverse engineer that by not using h but h bar. It's not important at all. Okay, and then, all right, so there you go. And so this is equal to the energy times the wave function. 2 pi lambda. Okay. Now, there's a few things to note. So notice that when I have this equation and I apply a wave function, I have this, and I'm going to call this an operator. Operators, it's really just a fancy term, but in this case it's kind of justified because you're doing a derivative, or a double derivative, and that means it changes the thing. And I can think of operating as changing. And so that's fair. So we call this we call these operators. And now, and I also mentioned to you, the hard part is, all right, so when I have this operator equation and I apply a wave function to one side, I have to apply it to the right side as well. So that's why I get this right here. So that's kind of brainless, right? You know, if I have A is equal to B, then B times C is equal to A times C, right? So it's like middle school algebra. So that's fairly simple. Unfortunately, it introduces a complication, which is that you can see that the double derivative of the wave function has to return a number times that wave function. And that means that we're working with the second order differential equation. And while this is fine with cosine and sine and e to the x and all that, there's many functions we have that will do this. As you can imagine, when we start including potential energy, this gets obscenely complicated really quick. Question?
Can you show where momentum squared and that top equation goes to in that second middle equation?
Everything but the 2m, right?
So how do we know that that's what it is?
Well, now, hold on. That's the subject of the entire last lecture, right? So, now at a very simple level, p squared over 2m still must be p squared over 2m. Here, let me apply the wave function here, right? So that, okay, p squared over 2m still better be p squared over 2m. The funkiness comes about. So why is minus h bar squared times the double derivative? Why is that momentum squared? It's because it's actually returning the de Broglie relationship. It's actually returning h squared over lambda squared. It actually does that. So Schrodinger's idea here was, of course, p squared over 2m is momentum squared. P squared over 2m is, sorry, p squared over 2m is kinetic energy. But to get it to be consistent with the de Broglie relationship, he's got to make it actually equal to p squared. It's got to be h squared over lambda squared. Okay, fine. Where do you get the lambda? Well, you get it from a wave function. How do you get it from a wave function? We're going to have to do things like take the double derivative, and that works. So yeah, it just plain works. The complications are, some silly ones, which is that you simply have to multiply by a minus h bar squared, because that also satisfies the de Broglie relationship. De Broglie says there's an h bar, there's an h in there. And unfortunately, you also set up a second order differential equation in the process. Because the operator for kinetic energy is a double derivative, you've automatically got yourself a second order differential equation. Again, last lecture. So, we're okay? Yeah, so again, I don't, I want to try to do my best to explain this without just being like, here it is. It is kind of traditional, to be blunt, to write this and say, here's the Schrodinger equation. Here it is, right? But there is some logic to it. It really is all about the de Broglie relationship, making sure the de Broglie relationship is satisfied. And I don't know if there's, maybe you can think of, well, what other ways could you do that? I don't know. I'm sure other people have thought of other ways to have something suck a lambda out of some other description, some model, right? Like when I'm doing this little mechanics here, notice that my model for the thing, the electron in outer space, is just its position. And if Newton is in the driver's seat, then all I need to know is where the particle is, and then I can get its energy. I can get its momentum, and then I square that its energy. So if I know where the particle is, then I have everything. Now, the reason that we're doing any of this is that this doesn't work for electrons. It doesn't work for things that are very light. It just utterly fails. It fails because there's no de Broglie relationship inside of this. Remember that de Broglie said matter has wavelength. Isaac Newton's classical things, wavelength? Where's wavelength? There's no wavelength in there. There's no wave. It's just a particle and it's moving. There's no wavelength. So how do you reconcile them? The answer is this. You get some model, instead of a model for position, this is your new model, and doing the double derivative satisfies the de Broglie relationship. Yeah. Another thing I'm going to do to you is actually work problem after problem. The reason I have so many homeworks is that it will help you accept this the more you do it, to be honest. Of course, I'm also concerned that maybe I'm showing you something that's completely wrong, which I'm not too worried about because I happen to know quantum mechanics is. So I shouldn't be telling you this at the beginning. Quantum mechanics is wrong. We actually know it's wrong. It is accurate to 99.9999%, not 100%. So we know it's actually wrong. But here's the thing, and I should not be telling you that. I'm actually going to show you what we think the right equation is about a month from now during the extra hour. It's not called the Schrodinger equation, it's called the Dirac equation. That's the real equation, by the way. But now let me ask you this. Are you okay with an equation that's right 99.9999%? No, you should be. Go away. Okay, so you need to be a theoretical physicist, the rest of you are chemists. Theoretical physicists, you're right. They're not actually satisfied with that. And that's why Dirac, who was really a physicist, developed the Dirac equation. And then that actually is a lot more accurate. But correspondingly, like a million times harder to solve. So that's why we stick with this. And also, seriously, 99.9999% accuracy on literally everything chemically you could ever measure. People are okay with that. Also, the Dirac equation, it's really similar. It's still a wave equation. And so that's why people have always thought, let's still teach the Schrodinger equation. It's still overwhelmingly used because it's still, I would call 99.9999% accurate pretty accurate. So, okay, move on. All right, so I want to just talk a little bit more about wave functions, and there's a couple of silly rules about them that the book teaches that you will see in most general introductory, this is your introduction to quantum mechanics, but I can't stand teaching things that I know are wrong, so I will show you the truth about them. So that's what I'm going to cover, but before I do that, as you have been doing in your homework, you notice that you've been dealing with this thing, which I'm praying you've seen this before, right? You have seen it before because I've had you do some stuff in your homework, but you should have seen this before as well. The square root of -1 is the letter I, right? So the square root of -25 is what? 5 times I. Okay, so I'm hoping that you've all seen imaginary mathematics before, and if not, you've had it on your homework. Okay, here's the deal. quantum mechanics is rarely taught using imaginary mathematics, but I do it. And the reason is that you have the pain of doing a little bit of learning on how to use imaginary numbers. The gain is that the questions you solve when you use imaginary mathematics to solve quantum mechanics, it goes from 20 pages to like 2 steps. So again, a little bit of a learning curve, but the gain is shocking when it comes to practically doing quantum mechanics. If you don't do it with imaginary mathematics, oh my God. Now the way that people resolve that who teach this class, they specifically do not cover the problems for which imaginary math gives you solutions in 2 steps. They just don't do them. Which again, I find that ridiculous. So, and also if you're not familiar, just tons and tons of homework problems will get you used to it. All right. Now you know that. Let me just write down a couple of properties of the letter I. I to the 0 is 1. Of course, we've just covered I to the 1 is I, like anything. I squared is minus 1. I cubed is minus I to the 4th is 1. Now, you're going to run into these a lot, by the way, so just heads up. It's not hard at all. Okay, but now, again, I want to point out the reason that this is useful is because of this. This right here is incredibly important. E to the ix. What this is let's write this out as a Taylor series centered at 0. And of course, the Taylor series of an exponential is 1. Then I've got the argument of the exponential. And then I've got the over 2 factorial. Then I've got the argument squared. And that's why that parenthesis came out screwed up. Argument squared over, I think, 3 factorial. Plus the argument, see I told you we're already running into, wait a minute. Yeah, I'm off, yeah, I see what you mean, right. So 2 factorial, 3 factorial, thank you, man. It's in my notes, but, okay, on and on and on. Okay, so what? Now again, I know you actually did this on the homework, but it's really terribly important. Okay, so this ends up being 1 plus ix minus x squared. Right there, looking at my notes because I might screw up, over 2 minus ix to the 3rd over 6 plus dot dot dot. Okay, so all right, now next trick. Next step. Okay, e to the ix. Okay, what you do now is you collect like terms. You end up with, now I'm going to write more terms than I put there just to prove a point. E to the minus x. So I'm putting all the real terms together. Plus x to the 4 over 4 factorial, 24. Okay. Then this is plus, I'm going to factor an I out, and then what have I got? I've got an x minus x to the x cubed over 6. Then I've got x to the 5 over, what's 24 times 5? 1, 2, 3, 4, 5, 121. Is that right? 24 times 5. No, that's not right.
120.
120. How did I? Oh, yeah, I know. Okay, dot. Is that? Okay. All right. So, what is this the Taylor series of? Left shark?
I would say cosine.
Yeah, it's cosine. Cosine x plus I, and you can already guess, or you can remember your homework. I sine x. Okay, there you go. Now, as you've already seen, when we do quantum mechanics, we have this kinetic energy, that's the double derivative. It's a second order differential equation. That means that when I set up a quantum mechanical problem I need to find something that I can take the double derivative of, and it's still there after taking the double derivative. Cosines and sines work, and a little branch of mathematics, linear algebra, which is way harder than it sounds, so maybe you've had it. Linear combinations of solutions are also solutions. So that means that if cosine is a solution and sine is a solution, then summing them is a solution, and that's an e to the ix. So again, I cannot emphasize how useful that is. And I also want to point out that you just, in the previous class, I gave cosine as an example of a wave function. And you now know that e to the ix plus e to the minus ix over 2. Now you did that on the homework. That is actually cosine and e to the ix. And you know, in all honesty, you might really want this memorized because you're going to use it. Now I have this in the cheat sheet. I have it on the cheat sheet. But this is absurdly useful. So you're going to need this all the time. Now remember, on the previous example, in our first foray into quantum mechanics, an electron in a universe by itself, cosine kx was the wave function. I can turn it into this. And I'm already thinking like, well, why the hell would I do that? This is obviously more complicated than cosine, and I'm quite used to cosine. I can take the derivative of cosine. The answer is, you have seen the first problem. Guess what the remaining problems look like? Begins with a C and rhymes with complicated. It's complicated. And this is going to be your best friend. This is going to be way easier than what we've got coming. So, and that'll be more and more clear as time progresses. Okay. Let me point out already, let me give you an early example of why this is incredibly useful. Okay, now here's another, now this is something of imaginary algebra, imaginary calculus that you may not have seen before, which is that if you have a function, and let me just call it a wave function, let's just call it a wave function, and it's imaginary, I've already told you that the absolute value squared is the probability density. I've already mentioned that last time, and then I gave you some examples trying to solidify that at the beginning of class. Notice that I did something funky. If I square anything, it's never negative. So why did I put an absolute value?
Because you have imaginary numbers.
Yeah, if I have imaginary numbers, then I actually need that, right? Because I can square something and get a minus sign. So that's to make sure that if I'm dealing with imaginary things, then that takes care of that. No negative probabilities, right? Oh, that sounds like a short answer question. Why do I have to take the absolute value of the square? Because you can't have negative probabilities. That's nonsense. Okay, so what about this? It turns out that this is easily evaluated this way. And who knows what this star means? What does that star mean? Let me ask you this. Let's do this. So I've heard, what do you say?
A compliment.
It says a complement. Now, what that means is, now if you haven't seen this before, it's very simple. Put a minus sign. Everywhere you see a minus sign, everywhere you see a letter I, put a minus sign. Okay. What about this?
So e to the negative I?
Is it minus e to the ix or e to the minus ix? Right, e to the minus ix. Again, go for the I and put a minus sign in front of it. Okay, what about this one? Oh, that'll get
So it
you.
would be
Yeah? What does the right shark say? What do you think?
Positive 1.
1 or minus 1, right? It's obviously, right, I squared is going to give a 1. Or is it a minus 1? I got a complex conjugate.
as long as I.
It's still minus 1.
Okay, here's how to do this. And actually, I don't remember. This is I times I. This is minus I times minus I. That is I squared, which is minus 1. Who's that? Is that right?
Yes.
Oh, yeah, that's right, there you go. I know, so right, I can throw some tricky ones at you. I can throw tricky ones like this. This almost got me too. Actually, I thought the answer was 1. And I have to walk myself through it. I always remember, when I run into a weirdo like this, I just do what you just saw. Put a minus sign in front of every I and then just go. Question.
So the minus sign doesn't go in front of constants, it only goes in front of I?
Yes, but but you could have 2I. I mean, I just put it there because 2 minus.
No, I get you.
Right? That get a little
And the
confusing.
square then should be inside the absolute value bars, right? At the top, if we're taking the absolute value of something squared.
Well, no. I'm saying you can do it this way.
No, but on the left-hand side, you have the absolute value, and then you square it. The square,
Yes.
Square
Yes.
should be inside?
Now I'm not sure.
Because you said you can get a minus sign if you have an I, but if you take the absolute value before you square it, that's defeating the purpose of taking the absolute value.
Oh, I know what you mean. I seem to have my notes as written, but that doesn't make it correct. I think I've written it correctly, but it's just symbology. Yeah, I'm not too sure, but I'll figure that out. But here's the point. You don't do this, you do this. I'll double check on that. You do that. Okay, last time, okay. Instead of a sine and a cosine, let's work with e to the I, let's give it a k, kx times x. Now, when I see that, k is momentum, that's 2 pi over lambda, but let's just forget 2 pi over lambda. I just don't like writing 2 pi over lambda a lot. And seriously, that's why we use the k in quantum mechanics. It's just a pain in the ass to write 2 pi over lambda all the time. So we give the k. Okay, so, and then I'm putting a kx because maybe at some point I'll have a y and a z. Anyway, now, if I want to make sure it's normalized, and I'm going to still do it this way, even though I'm not quite sure. What do? E to the I kx times x, e to the what? Okay, this to here. Sorry, I'm not writing it. It's that. Let me just put it.
Why do you use sub kx?
What's that?
Why do you use the kx?
So I have a k sub x. I'm just trying to get you used to the fact that when we have y's and z's, I'm going to have ky's and kz's. I want to go ahead and start doing that. I didn't have to. It's just a number. It's 2 pi over it's just like 5 meters to the minus 1. Anyway.
If
Okay.
it's the same number for x, y, and z, why do you have to have separate constant names for them then?
Well, no, who says it is? So again, when we get to wave functions in multiple dimensions, I could have different k's and different, those are momentums, right? So I can throw a ball entirely in the x direction, and the k and y and z would be 0. But I could throw a ball slightly catty-cornered, such that most of the momentum is in x, so that's a big number, but the k and y and z could be small. So anyway, it's not a big deal, it's just a label. I just want you to get used to the fact that we're going to have y's and z's coming up. Question?
Wouldn't that just be 1?
Huh? Yeah, right, back to this, right? What's that? What's e to the minus a times e to the a? E to the 0, what's e to the 0? Right. How hard is integrating 1? Not hard. Right, you see? You know how often, now this is, right.
It's actually x.
No, I have to integrate it, then I apply limits. So it's actually just a number. I haven't put limits. I have to put limits up here. I'm just trying to simplify. Anyway, look, my point being that if you're going to do this with sines and cosines, this can blow your head off. You put it in e to the x's, most of them disappear, and you just end up with 1. And that's way easier. And so if you want to stick with sines and cosines, that is going to turn into a nightmare really freaking quick. But you put them in e to the ix's, and then you see a little complex conjugate in minus ix. Everything gets incredibly easy. So I just wanted to point that out. Okay, so anyway, and another thing is to note that we're going to work example after example. Last bit I want to cover is, okay, so I I do want to show you what is traditionally taught in this class, but what is traditionally taught in this class is a simplification, and I don't like doing that. There have been the number of times I have intentionally misled you in this class has been, I can count on one hand. If you want to know the real truth, you have to go to grad school. Anyway, so there's these four stipulations on quantum mechanical things that that most textbooks will say that there's four things wave functions can't do, and they can't be zero everywhere. Okay, now this ends up being wrong. It's fine to have a wave function that's zero. What does it represent? Huh? What do you think a function that's just zero? What does that represent? It represents nothing, right? So it's fine to have a wave function of zero, it just doesn't represent anything. Now, if you're thinking like, well, okay, so that's useless. How useless is the number zero? Yeah, it's actually quite useful. So you actually do run into this all the time. So this is kind of wrong. Wave functions that are zero everywhere represent nothing, but we will run into this. Now there's another problem, and I hate to bring this up, but when you know, wave functions have to be normalized, and that means that the integral, I'll usually put minus infinity to infinity, and let's just stick with x for now. This has to be true. Now remember that when we solve quantum mechanical problems, we figure out the wave function without anything like the Schrödinger equation or a Boltzmann distribution. When we figure out wave functions just based on our gut, our nose, our general knowledge, they're not necessarily normalized, right? Cosine is fine, but that's not normalized. So when you write a wave function, let's do cosine. Let's do cosine kx, and this is for a particle in free space. Let's square it, and I know I'm not using imaginary numbers. There has to be a normalization constant that equals 1. Okay. Now, this is funky. Remember that we're going to spend a week on cosine squared, a particle, an electron in an infinite universe by itself. We are solving the wave function and going to do quantum mechanics on an electron in an infinite universe by itself. Because those are easy problems to solve and they're useful, and you figure a lot of things out. However, the universe is not composed of an infinite, this is not an infinite universe with only one thing in it. So it's simultaneously unrealistic. Okay, with that said, what do you think the normalization constant is? Recall that the integral of cosine squared, remember that cosine squared looks like this. Right? It's never zero, and it goes on forever. So what is the normalization? So what's the area under this curve that I just drew? Now again, the area under this curve that goes on forever and is never zero is infinite. So the normalization constant is what? Well, it's not infinite. It's 0 or 1 over infinity. Right. And that would technically make the wave function 0. Okay, funky, right? Now, the answer there is that this is a model problem that helps you understand quantum mechanics, but it is flawed because it is unrealistic and has an unrealistic normalization constant. So let's write out what a wave function should look like. A wave function should look like some function divided by the square root of the absolute value squared. Okay, so this is a normalized wave function. In the case of a particle in an infinite universe, the normalization constant, which is 1 over the square root of this scale, is actually 1 over the square root of infinity, which is 0. And that's like, well, that's weird, right? It's weird, but again, when it comes to a particle in the universe by itself, it's an example problem that's unrealistic, and the way that it's unrealistic is that it's technically 0 everywhere. When we solve problems, we actually don't, we cherry pick the problems that we solve with this, and we don't need to worry about the normalization, by the way. We always find problems to introduce you to quantum mechanics where this fact can kind of get swept under the rug. I just want to point that out to you, in case you ever realize that I've got some funky problem here. I do. It's an unrealistic example. But again, it is a great way to start, because otherwise, if I start with realistic examples, it's going to blow your head off.
So like when you integrate that whole thing, you get 1 from negative infinity?
Yes, you would technically get the number 1.
Okay.
Right? Because if I do this, you know, if I want to see if it's normalized, right, what I end up with is I have to square the normalization constant. I end up with the same expression on top and bottom, right? Yeah, they both technically integrate to infinity, so infinity over infinity is 1.
Oh, so what was the normalization constant in this case?
1 over the infinity square, 1 over the square root of infinity. And when I integrate the top part, which is infinity, I have infinity over the square root of infinity times the, I have infinity over the square root of infinity.
But you can't really evaluate that. You
There are rules to actually be able to do this.
Associated principle or other things.
The
Or no, sorry, the
L'Hopital's rule, right? There are ways to do this. So anyway, okay. Again, I don't want to blow your head off. I just want to point out to you math purists that we do have this slight problem with this example that we will spend the next week on. Okay, next one. I do need to power through this. Let's see, what else is there? About, again, wave functions, things that they can't do. I have to be continuous and smooth. And this is because wave functions are sort of probabilities. Because wave functions are sort of probabilities, and that means 2 things. Here on the y-axis is the wave function, on the x-axis is x. You cannot do this. You can't have the wave function fly off to infinity. Because again, probabilities can't do that. So no. You also cannot do this. You cannot do that. You can't have a discontinuity. No. You also cannot do this. You can't have a cusp. You cannot do that. Now, both of these 2 are due to the fact that they're when you integrate them, you need to output probability. This says, technically, you have a high probability to be in this spot, and simultaneously a low probability to be at this, whatever this spot is. It's x equals 1, right? High probability and simultaneously a low probability. No, probability never does that. You do not have 2 probabilities to be at the same spot, so that's why that's a no. So hopefully, you know, you can't have infinity and probability. You can't have 2 probabilities. This one's a weird one. This one's kind of interesting, and I'll end with this, and I'll finish the other 2 later. The double derivative with respect to space is kinetic energy. What's the double derivative of a sharp point? Well, I think you can give it a value. Technically, it's infinity. Right, so this wave function is of a particle with infinite amount of energy. You can't have sudden bends like that. It's like a car. Let's say a car is moving straight and makes a 90-degree turn, but I'm talking if you take a sharp turn, what happens to your face? Right? What if you took an infinitely sharp turn in a car? You would experience an infinite acceleration the other direction. It would smash you into the side of the car at the speed of light. The same thing is happening to a wave function with a sharp point. To do that requires an infinite turn, infinite kinetic energy, which does not happen. Okay, anyway, sorry about the 50 times 12. There's two other stipulations on